Good morning, pre-calculus students. I hope everybody's doing well. We're kind of in that halfway point of the semester where we're moving into new items in trigonometry and things. And so hopefully you're finding that transition to be fairly straightforward. Again, we're working mainly with the unit circle, and basically how it actually provides a very nice interpretation of graphs of the trig functions. And so that's what we want to do today. Last class, we talked about how we could graph sine and cosine, again, utilizing principal points and the basic shape of the parent functions. So what we want to do today is to talk about the other four trig functions that actually are generated from the sine and the cosine, get their parent shape, so to speak, get the parent functions for those, and then see how we can actually manipulate graphs using our basic transformations. Let me also just remind you that when it comes to doing the trig graphs, the basic transformations you'll always use. You don't want to overdo the utilization of calculus when you have very simple functions that you can understand using transformations. So these types of examples will actually do you a lot of good in the future. This is certainly an item that we need to cover and make sure you understand. And after that, we're going to have a short introduction to the inverse trig functions. This will be very important because this will be the only time that you talk about the inverse trig functions before we actually start calculus. And so we will do it in a piecemeal fashion. That is, we will restrict the domains of the trig functions and then work from there. And basically, again, utilizing the unit circle as our means of understanding the trig function. So again, what we do today is really important. And then, of course, after we finish the inverse trig functions, we're going to start talking about measurement along the circle, arc length, and degree measure, and move into some of the imposed triangles that I'm sure a lot of you all would like to be able to work with. So let me go ahead and share my screen. I want to go ahead and motivate the parent functions here. And what I've done, I've just done a really simple analysis here to show you how we can get the parent functions. And I wanted to provide this because it's very simple and it's based on the sine and cosine, which we've already understood. Now, one thing that we notice about the trig functions is that we know sine and cosine have period 2 pi, or any multiple of 2 pi is a period for sine and cosine. But the smallest real number, positive real number, for which sine and cosine are periodic is 2 pi. So that's fixed. So normally when you speak of a period, at least in the classical sense, you're referring to that smallest positive real number that allows the actual values of the functions to cycle. And so what we're going to find is with tangent and cotangent, because the way they're constructed, the actual period can be smaller. We know that tangent and cotangent will have periods 2 pi because sine and cosine do, but what we're going to find out today is that we can actually shrink that value. Now, how do we go about figuring out a parent function for tangent? What we're going to do is piggyback on the sine and cosine. And what you already see here is that we're going to get a principal branch that repeats itself over a period or interval length of only pi. And let me show you why that's the case. A very simple way to think about the tangent function is how we did when we were talking about the actual domain. And notice what we're going to do is we're going to look at the graph of sine and the graph of cosine and think ratio. So remember, tangent is sine over cosine. So when we think about the domain of the tangent, we have to avoid division by 0. So what I've done here is dotted vertical lines, x equal negative pi over 2 and x equal pi over 2. And so we can look at the rendering of the actual parent function for tangent based upon some graphical interpretations. So notice here, we have the sine of 0 and the cosine of 0. That's 0 divided by 1, which just gives us 0. But what we're seeing here is that we have a 0 of the cosine at pi over 2. I'll write this in, pi over 2. And so we're thinking, okay, that defines a vertical asymptote. But what's the sign, positive infinity or negative infinity? Well, as we approach pi over 2 from the left, we see that the sine is positive and so is the cosine. So again, the graph ascends to positive infinity. Now, of course, this is more of an interpretation graphically. It doesn't utilize any calculus. And so you're thinking, well, we could just plot a bunch of points, Professor Ron, and get the graph, but we're not really interested in that. So what we're going to notice is that we're taking two nice smooth functions and taking a ratio. And as long as we don't divide by 0, we get a nice smooth function. So the tangent function will also be smooth, which you won't be able to prove until you get the calculus to show that the tangent function actually has a derivative. That means that you can actually construct tangent lines at any point in its domain, but that'll come later. And then, of course, we look at negative pi over 2 here. Let me write that in. So this is something just like the sine and the cosine that you would probably want to put on a note card. You certainly have these functions in your ebook, in your Stewart pre-calculus ebook, which you can refer to, but it's nice just to draw them. And so now when we think about division by 0 here at negative pi over 2, that defines a vertical asymptote. But then what's the sign? Is it positive or negative infinity? Well, notice as we approach negative pi over 2 from the right, the cosine is positive, but the sine is negative. So that will assign a negative to infinity. So now the graph descends to negative infinity in the sense that it becomes infinitesimally small. So what we're seeing here is that because we're taking ratios and we only have basically the plus minus and the minus minus to work through the unit circle, we get repetition. That is, when you think about this particular segment here, 0 to pi over 2, this is in the first quadrant where sine and cosine are both positive. And then if you think of negative pi over 2 up to 0, that's in the fourth quadrant, where again, we have the cosine positive and the sine negative. And then of course, if we move to another interval right beside this one, pi over 2 to 3 pi over 2, we get the same sign convention because we're taking ratios. So all we have to do is just look at one particular interval of length pi, and we get the principal, what I call the principal branch of the tangent function. So this ratio construction to make the tangent function actually reduces the period of the tangent function. That is, there is actually a smaller number than 2 pi that will cause the outputs of the tangent function to cycle, that is to repeat. So now what we can see here, as I've labeled this the principal branch, when you want to graph a tangent function, all you need to do is just graph this branch. And then of course, the rest of the graph is just replication of this. You just put copies here and then to the left. So just like with the cosine and the sine function, we get one cycle. This is the only cycle we need to worry about for the tangent function. Of course, your WebAssign will probably print 2 or 3 of the branches, but you only need to identify one. Now, what I want to notice here is this is what we've already done, is just go ahead and write out the fact that we know what the domain is. That is, we don't want to divide by pi over 2. or any odd multiple of it. So we can add n pi. And what I've done down here is I've factored, like I've done before, the pi over 2. So all odd multiples of pi over 2 here give us the vertical asymptotes. So that really is what defines the domain. And then, of course, since we can ascend to positive and negative, or ascend to infinity and descend to negative infinity, we can get all real numbers as an output for the tangent function. So what you're seeing here is this tangent function is not half bad. It actually is on this branch 1-to-1, even though that's not a proof. We can look at this and say, well, Professor Ron, that looks 1-to-1. And what I'm going to ask you to do is to believe that. Again, in the calculus, we'll be able to prove that this is an actual 1-to-1 branch. And so now when we want to do the inverse trig function, we won't have to worry about restricting the domain. We'll just take this piece and then invert it, x and y, and get the actual inverse trig function. So that's going to make our process for tangent very simple. So again, what would you need to do? And when we do a graph, we're thinking, what are we going to need to do if we transform a tangent function? Well, we've got this nice little point 0, 0. I'll just put it right here. I wrote it over here to the side like I did the one for the cotangent. And then you've got these vertical asymptotes. So basically you have to see what happens to this point and these asymptotes. And if you like, you can take a point that's not at the origin, like maybe pi over 4, comma 1, just in case you happen to have like a reflection in the x-axis. So you'll get a free point that tells you basically where the curves actually lie, or the pieces of this principal branch actually lie. So this is less work than the cosine and sine function. So when you think about the tangent function, you've got to move the asymptotes, if indeed they move at all, and then you have to maybe move a couple of points here. And so an extra point that might be of utility would just be pi over 4, comma 1. We know tangent of pi over 4 is 1, so that's a real simple point to move. I often tell students, if you want to check one other point just to make sure you've got the correct graph, it's always nice to add this point into your computation. So it really is not as much work as the sine and cosine. So that's a relief. So when you think about the tangent function, you just think about copies of this red curve right here in an interval of length pi. So the beauty here is that we have a very simple function that's easier to remember than either sine and cosine. So the tangent function, even though I'm making it to be a friendly function, is ubiquitous in mathematics, and especially the inverse tangent function when you take calculus 2. And of course, probability theory will utilize the inverse tangent function. So it will come up over and over and over in your study of calculus, engineering, mathematics, and physics. Now, the other one that I want to do is the companion to the tangent, which is the reciprocal function, the cotangent. Now you're thinking, why don't I just reciprocate the tangent function in a visual way? Well, it's not as appealing as doing it just like I did over here. So I'm just going to approach this the same way since it's so simple to take ratios. Now, in this particular case, I'm defining the principal branch based on 0 to pi here. So 0 to pi. And again, because we're taking ratios, what we're going to see is that we can actually diminish the 2 pi to pi to get a complete cycle of the cotangent graph, just like we had for tangent. So the construction will proceed just like this one. That is, now what we want to do is look at cosine over sine. That is, the cotangent is the reciprocal of the tangent function. And so now here, we can just draw a little piece of the cosine function here from 0 to pi. Again, we cross through a 0 here of cosine at pi over 2. And then, of course, we actually draw the function for sine between 0 and pi. Now, what you're seeing in this particular case is that when we take ratios again, especially at pi over 2, we have 0 divided by 1. So we get a 0 at pi over 2. I've noted the point here, pi over 2, 0. I'll just go ahead and write that in, right by the actual point on the graph. And then notice we have zeros of the sine function like we knew before at 0 and pi. And therefore, we know that we have a vertical asymptote. And now how do we assign plus or minus to infinity? Well, when we approach 0 here from the right here, notice the sine is positive and the cosine both positive. So we assign the positive value to infinity. And for this asymptote or this approach, we ascend to infinity. So it looks like to be the opposite of the tangent. Now, as we approach pi from the left, what sign do we attach to infinity? This is Professor Ron's rendering. You're not going to find any of this in the book. My interpretations are based on my mathematical expertise, and they're easy, and they make sense if you think about it. And you can't even mess this up if you tried. So as you approach from the left, we see the sine of the cosine is negative. The sine of the sine function is positive. So that means we attach a negative sign to infinity and we descend to negative infinity. So now we get a nice principal branch that almost looks like a reflection of this one, though not quite because it's on a different interval. But just recall, the tangent function is odd, and so is the cotangent function. We get that for free. And then we're going to have odd and even for the inverse trig function. So that's going to haunt us, you know, as long as you're taking your STEM mathematics, which is fine because it's nice to know formulas for even and odd, even though they get a little bit more complicated with the inverse trig functions. So now what we can see is we have a nice simple graph of the principal branch of the cotangent function that runs from 0 to pi. So again, you're thinking, isn't this just like we had before, Professor Ron? So exactly. So the domain would exclude all division by 0. That is multiples of pi. A little bit less complicated than this one because this utilizes pi over 2. And then, of course, the range will cover all real numbers. And then, of course, the vertical asymptotes will just be multiples of pi. Remember, x equal n pi. Again, don't get sloppy on me. And I want to salute this class and all of my online on the schedule. You all are doing excellent work. You're working hard. You follow my directions. You take your test on time. You're just wonderful, and I appreciate that. But please don't get sloppy with the asymptotes. Remember, they're actual lines. X equal, again, a vertical line, horizontal line. So the important point here is just like I said before, when we talk about graphing a cotangent function, we're not interested in anything but replicating an actual principal branch. So we take this, and if we have to move it around or adjust it, we will. So of course, we're going to need to look at these two vertical asymptotes, just like we had for the tangent function, and maybe this point, and then of course, maybe another point, like maybe, again, pi over 4, 1. So we could also, I'll just go ahead and add this to the list, pi over 4, 1. So that always helps. If you flip the curve in the x-axis, then the point gets moved. And so then you know that the curve will have to look something like that. That just kind of keeps you from overlooking a reflection in the x-axis. Many times students will have a negative on the outside of the function, and they're only looking at 0, 0 or pi over 2, 0, and they don't see the reflection because the 0 is unaffected. So sometimes it's good to think of an additional point. But again, we always have to make sure that whatever transformations we encounter, that we have some way of reflecting that in the parameters that we're actually studying. So sometimes we might throw in an additional point. With sine and cosine, we have enough points that we don't have to worry. We've got those 5 principal points that keep us on the straight and narrow and don't allow us to make careless mistakes. Now, what I want to do is to go ahead and do an example of this, then we'll talk about the secant and the cosecant, which are even easier than this. But before I get to those, let me just do an example of a graph so that we can maybe take stock in what we have here while you're remembering it. So let's get an example. So for this one, I've just picked a WebAssign problem that looks like this. We'll just do a tangent function. So we'll say graph using transformations. Now, I don't think you'll see as many glitches in my document cam. I spoke with, well, I didn't speak with him. I just went online and spoke with the computer. But I changed my internet data plan, and it really didn't mean much different money. It just that when you have unlimited, it's not always really unlimited. You reach a certain data limit, and then they slow your speed. And so I don't think you'll see as many glitches. I can do like this, and it shouldn't freeze anymore. Or if it does freeze, it's just momentary. And so thanks to Xfinity. Nothing is free. Maybe one day, ladies and gentlemen, we'll enjoy free internet. We can keep our fingers crossed. So let's look at this. So say we have y equals tangent of, in this case, we're going to have 2x minus 2 pi over 3. Okay, so we want the graph using transformation. So in this particular case, we notice we're not going to have an amplitude in this case because these go off to infinity and negative infinity. So amplitude doesn't make any sense. But the shifting that we can do and the stretching horizontally and compression, all that vertically, that's still at play. So we're going to think of a k like we did before. So we need to factor. So we start with tangent of 2x minus 2 pi over 3. So we're going to factor that 2. And then we're going to see what happens to the asymptotes and any principal points. So we'll just have an x minus pi over 3. So again, what we want to do is just say, okay, don't worry so much about the actual objects that we have to move. Let's go ahead and map this out like we would have in college algebra. So now we have the parent function, tangent x, and we have a 2 here. So we're going to replace x with 2x, so that's going to be an h compression by 2. So again, everything's the same. We just really have less work to do, and less is good. We're happy for that. And then now we want to replace x with x minus pi over 3. So this is going to be a right shift by pi over 3. So this gives us tangent, and we'll have 2x. I'll just go ahead and use a bracket here. 2x minus pi over 3. So that basically defines what's going on. We just want to get an order that meets the requirements of the function, starting with the parent and ending with the given function. So now all we have to do is just move the asymptotes. And then of course we don't have a negative here, so we didn't reflect in the x-axis. So we'll just move 0, 0. So again, let's write down what we have. We have the principal, I call them the principal objects now because we have asymptotes too. So we have negative pi over 2, x equal negative pi over 2. We have x equal pi over 2. And we've got the point 0, 0. Again, we'll take an additional point, and I'll always remind you when we've got a negative outside of reflection. And of course, if you multiply tangent by a number, that'll make a small change, but they're marching off to infinity and negative infinity. So it's a minuscule thing to notice, but we'll still do it. So again, here, the H compression by 2. So we have to divide all the X coordinates by 2. So this will be X equals negative pi over 4. So again, we're going to shrink by a factor of 2. And then X equals pi over 4. And then, of course, dividing 0 by 2, no change. Now, what we notice here is that we're going to have to do some algebra here. So it won't be major algebra. We can just do it with each thing, so we won't worry about excessive work here. So now notice this is a right shift by pi over 3, so we have to add pi over 3 to each of the X values. So this will be X equal negative pi over 4 plus pi over 3. And we'll do the arithmetic. Let's just go ahead and write it down. X equal pi over 4 plus pi over 3. And then, of course, 0 plus pi over 3. Well, that's easy. That's just pi over 3 comma 0. So now let's just do a common denominator of 12. So again, this will be a 4. All of this is going to be with a pi, but we'll put the pi's in. So in this case, we get a 4 into 12, which is 3. So that's a negative 3 pi. And then, of course, a 4 here. So we get a 4 pi. So this is just a pi over 12. And then for here, we do the same. We have a 12. But again, now we'll have a positive 3 pi and a positive 4 pi. So this will be 7 pi over 12. Now, the thing that's important here is when we look at this and we think about this, it should give us make us feel good. So notice here we started with pi, then we cut it in half. That's pi over 2, and the difference between these two asymptotes is just 6 pi over 2, which is pi over 2. So we preserved that element of our computation. Now notice here we've got the pi over 3 comma 0, and so what would be nice is maybe to give it a denominator of 12 so it meets this criterion a little bit more easily. So again, we'll just go ahead and do a common denominator of 12. Well, I don't need a fraction bar that long. So we'll just do 12 and just have what, 4 pi. That way we can easily graph the principal branch. So now we have everything we need for a graph of one complete cycle, which will completely identify the graph. So let's do that. So go ahead and draw an x-axis, and we'll spread this out in copies of 1 over 12 or pi over 12. And the idea here is that if you do it this way, you've got a really nice, attractive graph that's easy to work with. So again, we've got a pi over 12, a 7 pi over 12, and a 4 pi over 12. So we can do like 1, 2, 3, 4, 5, 6, 7. So we can go ahead and draw this in. So this is x equals 7 pi over 12. And then the other one here, so I don't get ink all over myself, let me just do it this way. So we have x equals pi over 12. And then, of course, right in the center, we have 4 pi over 12. So 1, 2, 3, 4. So if you like, just do write it where we're not going to have to run through it. Now notice we can go ahead and extend this. Now, what we've done in this case, like I said before, we didn't do any reflection in the x-axis, so we don't have to worry about the graph flipping through the x-axis. So now we can take the shape of our parent function and draw. Okay. So here's our new graph relative to our transformation. And if you want, you can just put the tick mark here, 7 pi over 12 and pi over 12. So what this does is give a really nice graph. And so of course, if you wanted to go to the next one, this would just be add what, 6 pi over 12. So this will be 7 pi over 12 to 13 pi over 12. So you can go ahead and replicate and just add extra over here and extra copies of the principal branch to the left also. But this completely identifies the graph. So again, a periodic function with tangent is actually easier, but this is less difficult for us because we've already done sine and cosine. But just remember, when you're worrying about a tangent function or a cotangent function, you want to move the principal objects. And if you don't have a reflection in the x-axis, like a negative outside, then you don't really need to worry about moving any point except this. You know the basic shape. But again, you just have to remember, if you've got that additional point and you have a negative out here, then it's going to flip across the axis and remind you that the graph would flip. So that's the reason, you know, I'm trying to give you a little edge as to maybe doing a little bit less work when you don't have a negative out here. But when you do, you need to consider one additional point, or just keep it up here that the graph will be reflected. But that will not be something you'll see in the points if you don't have an additional point off the x-axis. So I hope that's clear. But what you're seeing here is that, ladies and gentlemen, this is a simple graph. We would not use calculus to graph this. That'd be a waste of time. We learned this in pre-cal, and we take all of this right to calculus because this will help us raise the bar. So when we start seeing the calculus, we'll see, oh yeah, I see why this function looks this way. I see why it's nice and smooth. I see why it's concave downward here, concave upward here. I see why they're vertical asymptotes. I mean, the idea is we're pushing the envelope to the extent that we can do everything possible without calculus. And that's quite a bit. So now you can kind of see how we can graph a tangent function. Pretty simple, huh? So now let's look at the secant and the cosecant as far as the parent graphs are concerned. Now, I did the same thing, but it's actually easier. Let me move this over. So here, I tried to do another Professor Ron did, and this seems to be fairly universal, doing the reciprocation in the most simple way. Now, here's the thing. We can't expect the secant and the cosecant to reduce as far as that smallest positive period because we're just reciprocating. So we're not taking ratios, so we're not getting overlap in values. So we're kind of stuck with the 2 pi here. So for tangent and cotangent, we can reduce that smallest positive real number to pi and actually get multiples of pi now for the period of cotangent and tangent. So that's actually kind of remarkable. 2 pi is still a period of tangent because it's a multiple of pi. But that actual smallest positive real number has been reduced from 2 pi to pi for tangent and cotangent. Now, when we think about secant, we think about just one complete cycle of cosine. So what I'm trying to do, ladies and gentlemen, is give you the principal branch. That is the branch that we will utilize to create a one-to-one function. And that's why I call these principal branches here. So here's what we do. we just take this piece of the cosine function right here, and let's see, what did I do here? Yeah, this is, let me be a little bit more clear here. Let me extend this so you can see. Here's the axis right here. Here's the y-axis. And that's, I need to make sure that that's really clear. So let me do this, because in here it's a little bit more complicated. Let me extend this one over here and go ahead and mark this off. So now look at this piece here. You're thinking, well, okay, I see what you did, Professor Ron. Normally, when we're graphing cosine with the principal numbers, we'll start here and go all the way to 2 pi. But what I've done is I'm focusing on the principal branch. So when we look at this and we see what we're doing here, we've got negative pi over 2, where cosine is 0. Then we have cosine of 0, which is 1. So we've just shifted things over. So we've got a complete cycle of the cosine graph. Now, again, this is what we consider when we're talking about the principal branch, for the principal branches for the secant function. So again, just look at this and think reciprocation. Okay, well, I've done 2 graphs in one. If we think about reciprocating 1, the output here, that's just 1. And if we reciprocate -1, we just have this. But now notice for this piece here, we have a 0 of cosine at pi over 2 and a 0 of cosine at negative pi over 2. And then when we reciprocate, we're thinking, okay, that's defining a vertical asymptote. What's the sign of infinity? Well, notice as we approach, in this case, from the left, pi over 2, and here approach negative pi over 2 from the right, the sign of cosine is positive. So we attach the positive to the infinity. And so the graph ascends. So we get what looks kind of like a parabola, but it's not. So the thing is that students even find these graphs easier because they just sketch in this little piece, this one cycle of the cosine function, and then they just smile and then they frown. So the key here is if we look at this piece, that is where we think about the part of the cosine function between these two zeros, pi over 2 and 3 pi over 2. Then we think, okay, well, you know, we've got this point pi comma -1, which is right here. And we think, okay, well, if we reciprocate -1, we just get -1. Now, if we think about, okay, well, what's going to happen when we flip this over? We've got division by 0. What's the sign that we attach to infinity? Well, when we look at this, we see that the cosine here is negative and the cosine here is negative. So as we approach 3 pi over 2 from the left and we approach pi over 2 from the right, we assign the negative to the infinity. So now we descend to infinity. So this is a very simple way of getting a quick graph of the secant function using the cosine function. Now, again, you know, you're thinking, okay, well, Professor Ron, we don't have any calculus, but at this point, we have a nice smooth function where the secant is defined. Again, a nice smooth function, not jagged. And the main thing here that we need to notice is when we think about this, just like we had before, it kind of makes sense that we have an upward concavity here and a downward concavity here. I mean, you know, intuitively that makes sense, but it's gonna really require some calculus to verify. When you have the calculus of sine and cosine, and then you move to secant and cosecant, as well as tangent and cotangent, you'll be able to verify all of this. So again, I wrote here principal branches because they're not continuous. That is, we've got this big old gap here. So you're thinking, okay, just like the tangent and cotangent function, these functions are discontinuous, but they are continuous on the actual pieces, so to speak. So instead of one branch here, we have two. We have an upper branch and a lower branch. And so what can we do to summarize the secant function? That is y equals secant x. Well, first, we know that we have to avoid zeros of cosine, which are just going to be odd multiples of pi over 2. And now, like I said before, the range is a little bit different. Since we're reciprocating, we've got this no man's land in between -1 and 1. So the range will run from -infinity to -1 here, and then from 1 to +infinity. So we get a gap in the range because of the fact that the cosine function is bounded between 1 and -1. That's the reason for the gap. And you can see this, at least in a visual, thinking about how we did this with graphs. So there's often a plus to looking at things, thinking about things in an intuitive manner, since we don't really have the calculus to prove any of this rigorously. And so now you're thinking, okay, so the vertical asymptotes we just get from the domain. So these would be the vertical lines, which are just x equal pi over 2 times odd integers. So again, negative pi over 2, negative 3 pi over 2, 5 pi over 2, 7 pi over 2, all x equal will give us all of those vertical asymptotes. But this is the principal branch. So when we think about graphing a secant function, ladies and gentlemen, all we have to do is worry about moving the vertical asymptotes if we need to move them, and then these 2 points here, which I've noted here. We've got the point 0, 1, and we have the point pi -1. So again, this configuration is a little bit more complicated in the tangent and cotangent, but what I usually tell students is just kind of think of the cosine curve so you can, kind of fidget around a little bit to remember what these are. You can think negative pi over 2, pi over 2, 3 pi over 2. And what we can see here is that the difference between these two vertical asymptote x values is just 2 pi. So we have to go an interval of length 2 pi to get a complete cycle. And of course, if we want it to look nice and not be all chopped up, we want to start here at a multiple of odd multiple of pi over 2. You can start here and just have all kinds of pieces of the graph, which would be one complete cycle, but it wouldn't look much. But again, that's the beauty of it. We like our pictures to look nice, and so we just choose the principal branches, so to speak. So again, this is really good to have on a note card so you can remember the basic pieces of it. Now, let's look at the cosecant function. Now, we do it the same way. Now you're thinking, is this a principal branch for a reason? Absolutely, because this is how we restrict for the inverse function, which is going to be kind of unique for this function. We're not really going to follow the inverse function of Dr. Stewart. We're going to follow the inverse secant function of Dr. Larson. That tends to be a little bit more standard. But again, it just really depends on the calculus book at A&M. When I taught the calculus labs, we used Dr. Stewart's calculus book, and so of course he didn't define the inverse secant the way I'm going to do today. But again, I always tell my students, check out your calculus book and see how they define inverse secant, just to make sure you're on the same page. You would think after this much time that the mathematical world would have decided on the standard definition, but I don't think anybody's worrying about it. I worry about it, but no one else does, it appears. So what about the cosecant function? How do we do it? Well, we proceed the same way we did for the secant. Now, again, remember the red graph here denotes the secant function principal branches. For cosecant, again, we look at sine in a principal type way. That is, we look from negative pi to pi. These two zeros are the sine function, which give us one complete cycle of the sine function. And just like before, we reciprocate in a visual manner. So just like before, if we reciprocate -1, we get -1. And if we reciprocate 1, we get 1. So at pi over 2, we have the value 1. And at negative pi over 2, we have the value -1. So this is thinking in terms of sine. So you never have to guess at this. You just kind of sketch it out real quickly and say, okay, these are the pieces I'm going to have to move. So again, we would think if we had to move some points, we'd move these two. Now, again, how do we figure out what the branches appear to be? We do the same thing we did before. Notice we're going to hit zeros of sine at pi and 0. And so when we reciprocate, these become vertical asymptotes. So then how do we attach the sign? Notice as we approach pi from the left, we have a positive sign, so we ascend to infinity. And here, as we approach 0 from the right, we have a positive value for sine, so we ascend to infinity. You'll never change this sign convention even when you get to calculus. It's the sign that controls the actual infinity behavior. Okay, that's a given. I mean, that's the beauty of real analysis. Once you master signs, that never changes, and you use it over and over again. What you learn about vertical asymptotes, you'll only heighten with some arithmetic, but the same procedure to figure out plus or minus infinity will be what you're doing right now. So this is it. Now, of course, when you think about this particular branch, as we approach x equals 0, that is, we divide by 0, we define, again, these two vertical asymptotes. As we approach x equals 0 from the right, we have a negative value for sine. And as we approach, in this case, negative pi negative pi from the, this was from the left and this is from the right. Sorry, as we approach 0 from the left, we get a negative. And as we approach negative pi, we get a positive, that is from the right, a negative. And so now all of this flips down. Sorry to get a little bit tongue-tied here. The idea here is that just look at the fact that as we have the right approach and the left approach, the curve of the sine function is below the x-axis. So like we've done over here, we ascend or descend to negative infinity in both of these cases. So we're seeing that the graph appears to look very similar, but it's shifted around because we know the cosine and the sine functions are just shifts of each other by pi over 2 radians. So the idea here is, again, we get a very simple graph based upon a happy face and a sad face. Now, again, like I said before, in calculus, you'll be able to show that this is indeed a true graph, that it's nice and smooth, no jagged parts, it's continuous where it's defined, and all of those good things. So as we summarize, again, we're going to want to move these 2 points and these asymptotes. And of course, from the division by 0, we avoid what multiples of pi. The range is the same, negative infinity to negative 1, 1 to infinity. And then, of course, the vertical asymptotes are defined by the zeros of sine. In this case, x equal pi times n. So multiples of pi. Now, like I said before, in both cases, the period does not change. The smallest possible positive real number for which we have the cycling of the actual values of cosecant and secant is 2 pi. So that doesn't change. And just to be very clear here, this is what we're saying. We've been saying this all along. Secant of x plus 2 pi times n will always be secant. Any multiple of 2 pi that you add, just like for cosine. So if n is equal to 1, we get 2 pi. And then cosecant x plus 2 pi times n will just be cosecant. So the idea here is that when n is equal to 1, we get that smallest value, 2 pi. But all of these are periods because we just cycle around and get back to x. So this kind of summarizes what we've been talking about from day one with the unit circle. So now let's do an example where we actually graph one of these types of functions. again, the graphing part is a little dry, I admit, little dry, but it's useful, especially when you're doing physics problems and engineering problems, to have a picture of things. So when you need a quick graph, just like when we were talking about the vibration of the tuning fork and the time, you know, how we were able to model that with a sine function. Again, that's very useful. So what I have here is an example for the secant function. And let's look at that. So what I want to do is say graph using transformations. Graph using transformations. And here, let's see. Yeah, this would be a good one. Let's do this. Let's do y. I'm gonna throw in a negative. They got a 1/3 outside. Well, yeah, let's do this. Let me try this. Let's do a negative. I'll just go ahead and throw in a negative. Negative 1/3. To just do a little one more transformation. Negative 1/3 secant. 2 pi x minus pi. So we're just kind of throwing everything in here. Now just before we get started, and let me click the let me move Professor Ron over a little bit. Let me refocus. Good. So notice it does glitch a little bit, but it's not as long before. They, you know, they Xfinity says that, you know, we don't slow for any reason, even if a lot of individuals are using our service. But it is an improvement. I just can't expect perfection. You know, as a math professor, we want everything to be perfect, and my music is the same. But we strive to do our best, and I'm sure Xfinity is trying to do that. So let's just kind of think back to what we have here. What are the objects? We're thinking we've got this x equal negative pi over 2. Then we've got x equal pi over 2 and x equal 3 pi over 2. That's kind of reminding you of the objects that we're going to have to move, and 2 of the points. So just kind of keep those in the back of your brain here. Now, first, what we want to do is make this a little bit more user-friendly. I threw in the negative just to make it more fun. So we have negative 1/3 secant, and now we want to factor the 2 pi. So we want the k, 2 pi. So this will be an x. And then, of course, we factor the pi, but then we need a 1/2 to absorb the 2. So here what we see is that when we multiply by the 2 pi, we get the 2 pi x. And of course, the 2 pi times 1/2 with the negative gives us negative pi. So that's giving us a shift. Now, first off, we can see that the period's going to change, but that 2 pi divided by 2 pi, that's going to be 1. So the period's going to be significantly smaller. And then, of course, we're going to have a vertical shrinking and then a reflection. So I've thrown everything in here, unfortunately. So let's first go ahead and do our transformation process. So secant x, chair shifts over. Let me do this. So we've got secant x. So let's start with the compression by H compression by 2 pi. H compression by 2 pi. You're thinking, Professor Ron, you could keep it simpler, but this will be good for you. Good example. 2 pi x. And then let's do a right shift by 1/2. So this is going to be a secant 2 pi, and then we replace x with x minus 1/2. So these transformations are really quite ingenious when you think about it. And then lastly, we're going, well, actually 2 more. We'll do a, if you like, a B compression by 3. And that'll give us a 1/3. And then lastly, x-axis reflection. So this will be a negative 1/3 secant 2 pi x minus 1/2. Okay, so we've got 4 transformations going on. So let's just see, again, we want a principal, the principal branches, just one complete cycle, that's it. So first, let's remember what we have. We have x equals negative pi over 2. We have x equal pi over 2. These are the vertical asymptotes, and x equal 3 pi over 2. And then we've got the points. We've got what, 0, 1. And then as we move over to pi, we have pi negative 1. Now, let me just remind you, remember our picture, x equal negative pi over 2, x equal pi over 2, x equal 3 pi over 2, and then we have the point pi negative 1 and 0, 1, which is what we have here. So when you compare the two, that's what I've written here. All right. So these objects define the principal branch. And since we're going to use the parent shape to get our final picture, this is all we need to do that. So let's go ahead and do this. So now we divide all the x coordinates by 2 pi. So I'll just write this out. So this will equal negative pi over 2. So this is just going to be 1 over 2 pi. I'll write these out so you can see them. And so the pi's absorb, and we just get negative 1/4. And then we have x. I'll do a little more arithmetic here since it's not as simple. 1 over 2 pi. And here the pi's absorb, and we get 1/4. And then we have 3 pi over 2 times 1 over 2 pi. Okay, now we see that the pi's absorb, and we get 3/4. Now, again, the new period is 1. So if we look here, the difference between 3/4 and negative 1/4 is 1. So that gives us the new period, which is significantly smaller than 2 pi. So this, don't scrimp on this, just work this out and you're good to go. So now we divide by 2 pi here. That one's easy. We just get 0, 1. And here when we divide by 2 pi, the pi's go away and we just get 1/2. All right. So that calculation was a little bit longer, but not difficult. Again, write the things out just to have something to check. And then now we do a right shift by 1/2, which we can easily do because if you think about it, these are easy numbers now. So if you would like, go ahead and do this. Before I do this, let me just go ahead and help you out. Think of the 1/2 as 2 over 4. Use that calculation. And I'll go ahead and translate this one. 2 over 4 for the 1/2. So now we add, in this case, we do a right shift. So we add 2 over 4 to all the x coordinates. So this will be x equals 1/4. So 2 plus negative 1 is 1. X equals 3/4. And then 2 plus 3, x equal 5/4. And then add 1/2. So we get, well, we might as well go ahead, since everything is in 4s, we might as well go ahead and put this in 4s. So that would be 2 over 4 comma 1. And add 2 over 4. So that's just going to be 4 over 4, right? Just keep everything in 4s, and then we don't have as much work to do. So now we're going to do a vertical compression by 3, that's not going to impact the vertical asymptotes, even though they have the vertical in them. That only affects the Y value. And there are no Y values in the equations of the vertical asymptotes, so they don't change. So just write them down again. You could just leave them alone, but let's just make the point that they do not change. And then of course here we get 1/3 for this, multiply 1 by 1/3. And then multiply -1 by 1/3. And then lastly, what we want to do is just do an x-axis reflection. Again, that's not going to affect these, but it will flip the y coordinates by applying a negative. So x equal 5/4. And then we have 2/4, -1/3, and 4/4, 1/3. So this defines the new graph. Now, again, if you're trying to shortcut your approach to this, you can, it's possible to do. But the first time you go through it, since I added some extra stuff here, it probably helps to write things at least a little bit more securely at first. And then you're sure that your picture of your complete cycle is correct. So now notice we have everything in fourths on the x-axis. So, you know, 1 to 1/4, 5, whatever, we can spread it out that way. And then 1/3 and -1/3. So we can spread this out also. So let's do an x-axis. So everything's been shifted. So now let's just say here, we've got, let's do, say, we've got a 1 here. So that puts like about a 1/3 right here, just kind of make it a little more real, so to speak. And then here, like a -1. So a -1/3 about right here. Just so we have maybe other tick marks on the y-axis. And then we have a bunch of fourths, so we can do 0, 1/4 up to 5/4. So 1, 2, 3, 4. So if this problem said, what are the new vertical asymptotes? Boom, you just have to move these and just do that part of the calculation. So let's go ahead and dot these in. So we have x equal 1/4. And then 3/4, 1, 2, 3. Again, when you put everything with the same denominator, it's easy. If not, you're just guessing, and I'm not asking you to do that. And then we have x equal 5/4. And now we'll just go ahead and do our graph in red. So we've got the point 2/4, -1/3. So here's 2/4, -1/3 right here. And then we have 4/4, 1/3 right here. So if you like, you can just mark this off as, let's see here, 2/4, and then 4/4. So I'm writing all these with the same denominator, so it's easier to graph. And then now, of course, we just connect. And do the same here. Just using the shape of the parent function. So there's our complete cycle. And then of course you can replicate this. You know, you can just, again, add, when you think about this, add another 4 here. So we get a 5/4 to 9/4 and just go this way, or do 1/4 to -3/4 and chop it up. So the idea is that with this, you can completely identify your function and you're good to go. You have one complete cycle. And what's nice about this is that all of this stuff is old. All of this stuff is old. And we didn't have to learn anything new. The only difference here is that with these functions, we have vertical asymptotes. And so you just have to remember the parent functions and how we constructed them. That's why I did them that way, so you could easily figure out what these are if you forgot. Now, of course, you can go ahead and like put these on note cards and to have to refer to as you work problems. I think that would be fine. So again, not very, not much pizzazz here, but certainly what you could see is that when you look at a function like this, say you're in a physics class, you look at a function like this and it comes in this package, calculus is not going to be very useful here. You're going to utilize your knowledge of the parent shape of the parent function, and you're going to think of it this way, and you can knock it out quickly. Again, the idea here is the process is longer or shorter depending on how much stuff there is here. And of course, if it's simpler here, then this is much easier. But I thought it would be good just to do something that has a little bit of everything in it. And again, just like we did before, get these common denominators. So when you go to draw your graph, you've got a nice clean graph that's separated nicely, and you can easily check that the period is confirmed. So that's the reason we do it this way, just so that there's no lapse in judgment when it's like, well, I think this is right. We don't have to think it's right. We know it's right. Okay. Now, what I want to do, and this is where everybody always moans and groans. We want to talk about inverse trig functions. And so, we just want to be able to say enough about these functions so that we can feel like we understand anything. That is, when it comes to inverse trig functions, we want to give an introduction that it will at least provide suitable preparation for the calculus. And that's what our goal is. Suitable, I like that, Professor Ron, suitable preparation for the calculus. So we'll just say 5.5 intro to inverse trig functions. And I know I'm being lazy. I'm not writing out trigonometric, but inverse trig functions. So again, what are we going to focus on? We can do all 6, but we're going to focus on 4 of them. I may mention the other 2, but if I don't have time, it's not that I'm discriminating. It's just that when you do your calculus, you basically focus on 4 of them, mainly 3, but 4 do come up. So I want to give you at least those, and then if we have time to say a little bit about the others, I will. Just remember that our version of the inverse secant will be what Professor Ron has given to you, and it will not be like the one in your ebook. That's not to confuse you, that's just to give you one that you'll be using in the calculus. And so that's important. So in the WebAssign, I think I focused on the actual formulas and things that I'll be sharing with you. So first, let's do number 1. We're going to start with the inverse sine. So for instance, inverse sine function. So when you think about note cards, this is a perfect opportunity to put these on note cards, because knowing these functions, at least in terms of parent function and basic characteristics, will be important. We're just going to basically be working the unit circle backwards. So what we're going to do is we're going to start with, in this particular case, y equals sine x. Well, and I'll apologize for this, but this is how we're going to have to start. And we're going to restrict. We're going to let x live between negative pi over 2 and pi over 2. That's what we're going to start out with. So what is that going to look like? We're going to make it 1 to 1. So this is a universal convention here. So we'll do our pi over 2 and the negative pi over 2, and we'll have a 1 and a negative 1. So I'm just drawing the piece of the sine function that will be 1 to 1. And it'll look something like this. We're just looking at this piece. So that's of course, we can keep going like this and going this way. So this is the restricted sine function. So restricted sine function. So again, we would need the calculus to prove that the function is actually increasing here and that it would be 1 to 1, but we don't have that. So we have the parent function, and you have Professor Ron's word that the sine function is increasing here, and it is therefore 1 to 1. Doesn't double back. So 1 to 1. So the restricted sine function is 1 to 1. And this is universal. This is not up for debate here. This is the universal restriction. And so now we want to flip everything. We want to reflect this graph in the line y equal x to define the inverse sine function. How do we write it? So we define the inverse sine function, and we'll use the same lettering. We're going to define the inverse sine function. So we're going to say now y equals inverse sine. Now there'd be two ways to write it. I'm going to use the -1 usually. Dr. Stewart and Dr. Larson sometimes will use arc sine. So we'll use sine to the -1 and also arc sine. You'll see it both ways. Dr. Larson likes to use arc sine. I prefer the -1, but you'll see it either way. So be flexible, no problem. If it's written more this way, then yay. If not, don't. When you see arc sine, know that it is equivalent to this. And this will mean the following. Let me do this, where now the x's and the y's have flipped, x lives between -1 and 1, and the inverse sine lives between -pi/2 and pi/2. So we've just defined a reverse path. This is what we call the reverse path. So if we reflect this in the line y equal x, we can get a picture of the inverse sine function. And of course, it's going to have vertical tangents at -1 and 1. So here we've got -1, 1, pi/2. Excuse the scaling, I'm just trying to make it look pretty. -pi/2. So just flip these points. So this will be -1, pi/2, the flip of this point right here, and then 1 pi/2. So this is the function y equal inverse sine, where we're using the independent variable x. So now what we're seeing is when we reflect this in the line y equal x, and we basically flip the range and domain here, we get the new domain is -1 to 1, and the new range is -π/2 to π/2. That's the inverse sine function, and it's nice and differentiable except at 1 and -1, where it appears that you've got vertical tangents, and you do. So once you establish the calculus here, you'll establish that that's a horizontal tangent here. So this will become a vertical tangent and a vertical tangent. So the calculus will solidify all of this, and you don't have to believe me. The calculus will say, okay, this is true. And again, if the 1-to-1 function is increasing, so is the inverse. This again appears to be increasing, just like that function. And so again, we have inverse equations. So number one, we'll say sine of inverse sine equals x if and only if x lives between -1 and 1. It's got to be defined basically based on this. And then two, the inverse sine of sine of x will be equal to x as long as we obey the domain of the sine, or the range of the inverse sine. So this has to be in the output, so to speak, of the sine. So this will be x element -π/2 to π/2. So when we look here, the inverse sine must obey its range. So we've got this. And here, the inverse sine must obey its domain. So we have this. So these are very simple, but we can't be as free as we were before. That is, now when we do the composition of the function with its inverse, we do get the identity as long as we are careful to regulate the inputs of x in both cases. So that's basically why it's important to know this graph. And if you know this graph, you can do this and you can do this. So this is our construction for the inverse sine function. Now let's do the same for inverse cosine. I'll just do this on a new sheet so I won't run out of room. So commit to memory. The inverse cosine, let's do that one. We'll call this one 2. Define it the same way. Inverse cosine function. Oh, and I'll add another little deal here. This is important. The inverse sine function is odd. So this we will use inverse sine of the additive inverse of x is the additive inverse of inverse sine. So that's a little tidbit that we'll use. This is an odd function. Not all of them have these nice properties, but the inverse sine, again, the picture looks like we've got origin symmetry. Well, that's not a proof, but at least you could believe this. The proof we could do analytically, which would not be difficult. We may look at that later. I have some other proofs that I want to do eventually once we get these at least solidified. So now for the inverse cosine, we do the same thing, and this one is also universal. So here we're going to say y equals cosine x, the regular, but we're going to restrict, where we're going to say x lives between 0 and pi. So we're going to do a 1-to-1 function, create one by restricting the input of the cosine function 0 to pi. So what does that look like? So we have 0, we know we get 1, and then pi over 2, and then pi. Negative 1, 1. So that's the part of the cosine function that's restricted. So this is y equal cosine x restricted. This again is universal. This is 1 to 1. Now again, we know in this particular range or domain of the cosine function, the calculus will prove that the cosine is decreasing. Even though I've drawn it like it looks decreasing, we don't really know that without the calculus, but the calculus will prove that this is a decreasing function on this interval, and therefore 1 to 1. So now we define the inverse cosine. So define, so we basically now reflect this graph in the line y equal x, define inverse cosine function. This is remarkable stuff because the calculus of these inverse trig functions is very rich. I mean, this is one way to do it, and it's a very intuitive way to do it that's going to help you in calculus. So we're going to say y equals inverse cosine, in this case, of x. Now, there's another way to write this. It's called arc cosine. That. And just like I did before, x between 0, well, let me put the 0 here, 0 and pi, because now everything's going to flip. Oh, sorry. Everything's going to flip with you negative 1 to 1, just like we did before. The math always tells you what to do. And then the inverse cosine, again, it's going to flip. We'll live between 0 and pi. So again, when we look at this, what's the picture look like? Well, let's just flip the coordinates here. So now we've got negative 1 to 1. The thing that calculus repeats with just negative signs, that's why we only really focus on 3 of them. And then we'll have pi over 2 and pi. So now the x's and the y's basically flip. And so now we take the flip of this, which will be negative 1 pi. And we take the flip of this, which is just 0 pi over 2, because right there is pi over 2. And then the flip of this, which is what? 1, 0. And so we can draw it. So vertical tangent. So here's the inverse cosine function. Let me make it a little bit darker. So this is y equal inverse cosine. And I'll use the -1. Again, remember, both of these are used widely, the -1 and the arc cosine. They are equivalent. So don't be shocked if you see this or you see this. They're both equivalent. The notations are used widely. And then, of course, we get the inverse equations. That is, I'll do it the same order, cosine of inverse cosine of x equals x, but we have to obey the domain of the inverse cosine. So this means x lives here between -1 and 1. And then 2, inverse cosine of cosine of x should also be the identity as long as we obey the output of the inverse cosine, which is 0 to pi. So this is, WebAssign loves to give you problems like this where you know, this has to be well defined, but this could be actually an x outside of this, and then you have to adjust it with a reference angle or something. And yeah, so all this stuff about reference number and all that, boom, you know, it's still there, and you all are doing well with that, even though I think it's sometimes a thorn in your side. It's almost like when I look at what you're doing with the quizzes, you seem to have gotten it. So I salute you for your industry. Now, one thing that's not as nice about the inverse cosine is that it doesn't have the odd bit, but we can do a inverse cosine of the negative argument. And this is actually pi minus inverse cosine of x. So this is a little bit more complicated, but we'll use it. That is, it's not an even function, it's not an odd function, but it can be addressed this way. Again, this is not difficult to prove. You can think of it in terms of manipulating the graph if you like, but I find when I don't give this to my students in pre-cal, they go crazy. It's like, inverse sine is odd, Professor Ron, but what about inverse cosine? So I just started saying, okay, we'll do this, and you have time to prove it, fine. If not, use it. The beauty of this is that if we have to negotiate a negative input, this allows us to do it. So the inverse cosine, the actual derivative of the inverse sine is the additive inverse of the derivative of the inverse cosine. So we really only focus on the inverse sine in calculus, but we drag this along for the ride. It's just when we make up the integral tables, this one kind of gets left out because negative signs aren't that big of a deal for us in calculus. So again, inverse cosine. Now let's look at the inverse tangent. Now commit to memory, commit to memory, commit to memory. I'm sorry, but I commit to memory. So the, excuse me, the inverse tangent's easy. So we'll do this. I'll use the same setup, inverse tangent function. You're thinking this is easy. Well, it is as long as you obey the range and domain, we're fine. Now, the secant will be a little bit more complicated, but it'll be doable. Now, the tangent, like I said before, is simple. We don't have to restrict anything, or we don't have to be clever about anything. We're just going to say y equals tangent x, and we're going to allow x to live between the two vertical asymptotes, so to speak, negative pi over 2 and pi over 2. We already showed you today that that's a nice increasing branch. The calculus will verify it. You'll say like, well, it looks like it's increasing, Professor Ron. Looks like it's increasing? What does that mean? Well, absolutely nothing, but the calculus will prove it. You know, it's like when I have these conversations with you, I'm like, okay, kids, a to the x has positive output, and you're thinking, okay, well, that seems intuitive. Well, you won't be able to prove it until you get to calculus, because you're going to start with the natural log function. And basically, when you actually flip the range and domain, you get the positive nature of the output of the base A exponential when you do it the correct way. So that's just life, unfortunately. So x equals pi over 2, x equals negative pi over 2. So remember, this is a nice increasing branch. This is our friend. So this is the restricted. Well, it's not restricted, it's just the principal branch. So this is y equal tangent x principal branch. We didn't, we just took that piece, principal branch. So it is restricted because we're only looking here, but it's nice, restricted. And so now the vertical asymptotes, when we reflect in the line y equal x, become horizontal asymptotes, and we're done. So define the inverse tangent function. So we'll use the same independent variable just to keep everything on the up and up. Even though I don't like to do that, it keeps you from losing your sanity. So we'll say y equals inverse tangent of x, and it can also be written arctan of x. And here, and this is what's interesting about this, the range is negative infinity to infinity. So you're thinking this is a very user-friendly function. We just split the range in the domain, the range being all real. So now the domain of the inverse tangent function is all reals. And so now we can have the inverse equation. So this is much more user-friendly. Students like inverse tangent. They never make mistakes with inverse tangent. So we'll do tangent. I just want to do these in the same order as I've done the other ones. Inverse tangent of x equals x, as long as we obey the input of the inverse tangent. So if and only if x is just a real number. So you can't really mess that up, can you? And then 2, inverse tangent of tangent of x will be the identity function as long as we obey the output. The output will lie between negative pi over 2 and pi over 2. So here's the gift for the inverse tangent. It's odd. So you're thinking, yay, don't have to work too hard for this one. I'm not kidding, folks. You need to learn these and know them and then work the unit circle backwards to get the values. You will come to grief a little bit with this, but it's worth it. It's okay. It's going to take a little while, like adjusting to the unit circle. Now, again, the picture of this is just flipping this in the line y equal x and making now the vertical asymptotes into horizontal ones. You know, the analysis requires understanding of the inverse trig, all the transcendental functions, and then as you work into other forms of integration and all, and so this is your bread and butter, especially you future engineers or future anything in STEM. So now we have y equal pi over 2. So now these vertical asymptotes become horizontal. And of course, this is an increasing function. So the inverse will also increase. So this is a favorite of my students. They like the inverse tangent. And it's useful in calculus. Vertical tangent. So here's the inverse tangent function. Okay. So like I say, you can think of how we restrict, and then all this part you need to know, because this is defining the inverse tangent function for you right now. This is your definition of inverse tangent. And just like tangent, you can only use the unit circle for specific values. You'll know some exactly, and others you're like, okay, well, I'll write down the symbols for it. And then the calculus will help me out with approximations, especially if Professor Ron needs to use the Google calculator to maybe approximate the inverse tangent of what, 3 or something. So the idea is at this point, this is your definition. learn it, okay? And this, again, abide by the ranges here, the inputs when you do these. These are all, make great WebAssign questions. Now, the last one that we're going to focus on will be the inverse secant, which will be my definition, because I want you to know this for calculus. So we're gonna restrict this in a way that I use when I teach calculus at Sanjay. So now we'll do the number 4, inverse secant function. This definition preserves the reciprocal inequality, and it makes the derivative of the tangent all positive. You get an increasing, you basically restrict so that the secant function, inverse secant function, is increasing. So we're going to say y equals secant x, and we're gonna get clever here. We're going to say that x, in this case, lives between 0 to pi over 2. And of course, that's a vertical asymptote, so we're going to parenthesize, so to speak, union pi over 2 to pi. So what's that going to look like? Let's draw it. So this is the restricted version. So restricted. Here's pi, x equals pi over 2 and 0. And we'll put 1 and negative 1. So I'll draw it. This piece here. So basically, we restrict, so this is y equals secant x restricted. We restrict the function this way so it's increasing. So this piece that we restricted appears to be increasing. Well, it is. The calculus will reveal that. So our inverse function will necessarily increase. Again, I'm giving you the construction process that mathematicians come up with for reasons of convenience and for usability. Okay, and so again, this isn't something that someone just woke up one morning, okay, I'm just going to define inverse secant to be this. This is something that's studied, and mathematicians come together working with scientists and engineers and people in the STEM, even before we called it STEM, to come up with conventions that are worthy of the academic process. And so now what we do is we just basically flip this in the line y equal x and define the inverse secant using this particular set of pieces. So define the inverse secant function. So we're going to say y equals inverse secant. We can do the -1, or we can do arc secant. You see it both ways. I want you to be familiar with both ways. You look in the Larson calculus book, you'll see it written arc secant. But of course, with the WebAssign, the kids can write it with the -1 too. I think Dr. Stewart likes the -1 better, but get used to seeing it this way. As you look through the literature, you'll see if you go to Wikipedia and the inverse trig functions, you'll see this. Now, we make this restriction where x lives where we think it's going to have to live. Now, what's important here is now the domain is here, so it's like what? Negative infinity to -1, and then 1 to infinity. Now, of course, if you wanted to get lazy, you could also write this as the absolute value of x is just greater than or equal to 1. That's another way to write it. But most students, if they've got to move it up to here to interpret it, they rather just write it that way. That's just another way to write it if you want to save some time. But the visual is a little bit better when you spread it out, so to speak. Okay, so now again, we're thinking of the inverse function having the domain, which is the range of the secant function, just like we've constructed many, many times before. So all of the techniques that I'm using are things you already know. We just now are utilizing, new objects. And so getting used to secant, and now we have its inverse. Now, what are the inverse equations? So number one, with the same order, we'll have secant of inverse secant. Again, as long as we obey the domain, if and only if x lives here, negative infinity to -1, union 1 to infinity. Again, this is different from the Stewart definition, so don't use that. I apologize, but Stewart and Larson don't agree on their definition of inverse secant. It's unfortunate, but that's just the plague of mathematics. Inverse secant of secant x. So we have to obey the output of the inverse secant, which will be 0 to pi, throwing out the pi over 2. So what I've tried to do here, ladies and gentlemen, is give you all the ingredients, again, using x as the independent variable, so we can think of using that reflective property to keep from, losing our minds. And then, of course, the inverse secant, it's actually pretty good. It's got two nice little rules I want to give you with this definition. We know that the inverse secant of x, this is called the reciprocal rule, is basically the inverse cosine of 1 over x. That's a nice little identity that is one of the byproducts of defining the arcsecant by this definition here, and I'll draw it. And also inverse secant, it's not odd, but it looks like the inverse cosine of the negative argument will be pi minus the inverse secant of x. Again, two little identities here that are very useful. This is called the reciprocal rule, which is true because of the way we defined it. Well, let me put it on the other side so my graph doesn't run into it. This is called the reciprocal rule. Dr. Larson always brags about this. Well, with my definition, we get the reciprocal rule, and I agree with him. It's useful to have. He's a wonderful person and mathematician. Like I said before, I did have the opportunity to meet him. And he's done great things for the education of STEM students and math majors throughout the world. Okay, so let's draw it. It's going to be a nice increasing function. So remember, our vertical asymptote becomes a horizontal. So we can mark off pi over 2 and pi. So all the little techniques I taught you before, I'm using now, or reminded you, you actually learned them in college algebra. And so now we've got, this is 0, 1, so we get 1, 0. And then of course we converge to this asymptote in an increasing fashion. That's how you can never mess up the graph. You know it has to increase, so it's a little branch like that, because that's increasing. And now for the other one, we have, we're going to have what, -1 pi. So here's the -1. So -1 pi is up here. So -1 pi, and we have to increase to that. So if you follow my construction process, you'll never mess up these graphs. If you don't, then your graphs will always be wrong. So do what I do. So this point, this is a little bit more complicated. This is -1 pi here. So this is inverse secant. So what's important here, ladies and gentlemen, is that now you're thinking, well, you know, do I even care about this? Well, I'm going to show you some really, really nice tricks later on as we move into chapter 6 that will continue these ideas. And we're going to see that there's some really nice algebra that goes on with all of this. For instance, now what we can see is that we get basic inverse equations with all of these. That is, then x is just the secant of y, right? If we flip it around, just like the logarithm in the base a exponential. And we get these nice inverse equations. So this completely defines our inverse trig functions for now. I may add some more things later, but what I want you to do is to commit all of this process to memory. Put on a note card so you know the graph. This is the graph we're going to use for inverse secant. You'll use this in calculus, and use the construction process. Now the thing, as you look at your WebAssign, what you're going to see is when you actually evaluate the inverse trig functions, you're just going to be taking the unit circle and working it backwards. So if it's not a point on the unit circle with a corresponding measurement along the unit circle, then you just write it as it is. You just leave it alone, write it in terms of symbols, like writing pi, the Greek letter pi, for the ratio of the circumference of the circle to its diameter. You know, if we want the actual value, we have to use the Greek symbol. Otherwise, we have to be happy with an approximation. So let this sink in and put these on note cards. And then what we'll do on our next lecture, we'll do a little bit more work with the inverse trig. Then we're going to talk about degree measure and arc length and things like that, which are going to be kind of a lot of fun. Sector area. I mean, I'll just say this, the first section of chapter 6 is fun. You'll enjoy it. It'll be like taking physics. And students tend to like to have a nice little break, because this is going to take some time. You need to spend some time on this so that you have mastery of it and that you have the basics down. And so, like I say, we'll say much more about this, but like I say, the inverse secant, inverse tangent, inverse cosine, inverse sine. Now, if we have time, we may mention the other two, but they're not going to be as important for our study, but I want you to focus on these for now. And again, just remember, this week I'm starting to make things do a little bit later in the week to give you a little bit more flexibility, so maybe you don't feel as rushed. I appreciate the fact that you all complete your assignments, that you stick to the deadlines, and you are conscientious about your work. In this time that we're living now with COVID, it's very difficult to keep everything in perspective. And I appreciate your industry, and I appreciate the fact that you're taking your work seriously. So have a great day, and get some rest. I'll send out an invitation for conference hours today if you need those. Otherwise, I'll see you on Thursday. Take care, everyone.
Have a good day, sir.
Bye.
Thank you.
Thank you. Enjoy inverse trig.